Hello, everyone, and welcome back to vians.org. The problems that what we're going to deal with in today's class is a continuation of what we had done earlier. That's real number. We were dealing earlier with real numbers, part two, that's chapter one of your CBSE math curriculum. So we were working with part two of your real numbers, which was basically rational and irrational numbers, and we'd done a basic problem, but we had gone through the concept of what was a rational number and irrational number. So if you've not seen that class, please go back, and it would be good in case you had a look at that class. But that's where we will be continuing today. So today what we'll be doing is I've taken a few problems from your previous CBSE papers, and I thought it would be a good exercise to go through these problems one by one. Let's do that now. Let's get to it right now. So the first problem that we'll be working with is this. Express, so this is sort of like a recurring number. Express 0.166666666, which is a non-terminating number, as a rational number in its simplest form. So we've got to represent this as a rational number. So to continue with that, we first of all need to express this in a rational form. So we know that this is a non-terminating number which will go on with the 6666666 forever. So let's say that x, this number is called x, and it is equal to 0.1666666, and so on and so forth, and this is our equation number 1. Now let's multiply both these sides by 10. Alright, so what would that be? That would be multiplying 1 by 10, we get 10x is equal to 1.666666, right? 2. Now basically the thing is, we need to subtract one terminating number from another one non-terminating number from another non-terminating number with the same digits in the decimal places, so that we would get a whole number or something that would be in a terminating form. So for example, if I now reduce this, it could be like if I do 1.666 minus 0.16666, it'll be 1.5, right? This another way of doing it is, we could always multiply 2 by 10 as well. So multiply 2 by 10, we get, that's 100x is equal to 16.666666. Alright, so now we could do, and this is your 3. So now what we could do is 3 minus 2 is equal to 100x is equal to 16.6666, so and so, minus 10x is equal to 1.6666, so is equal to 90x is equal to 15.00, right? So sorry, so this can be written as x is equal to 15 by 90, which is nothing but you can divide this by common factors. So 5 3s are 15, 5 1s are 5, 5 so 5 is a 5, 6 4 remains, 5 8s are 40, and we know 3 goes by 6, 18 divides by 3, and you get 1 by 6. So 0.1666 can be explained in its rational form as 1 by 6. And remember, in CBSE papers, this always process always deserves some credit. So follow the steps that we write, try to make it as easily understandable as possible, and as far as possible try to mark the solution in a way that the examiners would find it easy for you to for them to understand. So that's something that we've solved. Just in case you're having a difficult time understanding my handwriting, that's the same thing that I have written over here, so that it would be more easier for you to understand. So we've done the same thing. X is equal to 0.166, multiplied it by 10, multiplied it by 100, subtracted 2 from 3, and we got 90x is equal to 15. So we got 15 by 90, that's 1 by 6 is equal to x. All right, so the next one is the next problem. Let's go to the next problem. The next problem is 0.254545454 as a fraction in its simplest form. If you see over here, this is a slightly, this is different from the previous problem, because the previous problem dealt with a number that was non-terminating, true, and this is also non-terminating. So it was non-terminating, but it was non-terminating with the same digit. Over here this is slightly different because it has two numbers that are alternating to make it non-terminating, but we're going to basically follow the same approach. So basically consider x is equal to 0.254 54 on and on and on, and this is your first equation. Now multiply 1 by 10, we get 10x is equal to 2.54, and that's 2. We could also multiply 2 by 10, and we get 100x is equal to 25.454545, right? So right now if I could subtract this, if I could subtract this from this, I would still get a very, if I subtract 1 from 2, I would get like what, 2.3, 29 something. I would go on and on forth because these don't exactly cancel. See, 5 and 2 comes along, 4 and 5 will be subtracted, 5 and 4 will be subtracted, 4 and 5 will be subtracted, it will go on and forever. So again we multiplied by 10. Here this is a necessity. In the previous question, if you remember, it was just like you got a 1.5, you got a terminating decimal in the second option itself. Here you won't get a terminating decimal, that's why you're just multiplying again by 10. Now I've got 25.45. You can't subtract this from this, because again the same problem will happen. The numbers don't line up. This does line up, so you could say 25.45 minus 0.2 is going to get what, 25.2. It's going to give you 25.2, and then it's 100. But anyway, you will have to convert it into a decimal form. So if you just see, multiply 3 by 2, sorry, by 10, we get 1000x is equal to 254.54. So sorry about that. So now if you see, this is 4. So irrespective of whether you do 4 minus 2 or 3 minus 1, what are you going to get? Okay, so if you did 4 minus 2, what would you get? 4 minus 2, it's very easy to say. You would get 1000 minus 10. So 1000 minus 10x, 1000x minus 10x, and then you would get what, 254.5454 minus 2.5454, that would be 252. That's one way of writing this. Or you would also get, if you did 3 minus 1, you would get 100 minus x, that's 99x is equal to 25.4 minus 0.2545454. So 25.4 54 on and on and on. From here everything will subtract. So from here everything will fall in line. See, this 5 and 5 matches, this 4 and 4 matches, this 5 and 5 matches, this. So on the second decimal place you have 5 over here and 4 over here. Third decimal place you have 4. Fourth decimal place you have 5. So everything will cancel from there. But 25.4 minus 0.2 will give you 25.2. So x by extension is going to be 252 by 990, or 25.2 by 99. Either way, you're still getting the same answer. So irrespective of how you solve this, you're still going to get the same answer. Now let's simplify 252 by 990, because that's what we would have done. We would have multiplied this by 10 on the top, the numerator as well as the denominator, to get 252 by 990. So now let's divide by 252 990. We know that both of them have 2 in common, or actually 5, 6, 7, 8, 9. Both of them have 3 in common. So 3, 7, 3, 8s are 24. Okay, and remaining 1, 3 4s are 12, and 3 3s are 9, 3 3s are 9, 0. This is 8 plus 4, 12. This is 3 again, so this can be again divided into 3 2s are 6, 3 8s are 24, and 1 1 0. Alright, now this is again ending in 2, so you can further simplify this. 2 1s are 2, 2 4s are 8, 2 5s are 10, 2 5s are 10. So this is 14 by 55. And 4 plus 1 is 5, 5 plus 5 is 10. You can't simplify this anymore. 7 won't go here. Any other factors of 14, that's 7 and 2, won't divide. This has 7 and 2 as its factor, and you know that this has 5 and 11 as its factor, so you're not going to get it any simpler than this. So this is the solution. This is the simplest form of form in which 0.254545454 non-terminating decimal can be explained in as a fraction. And if you see, just in case you don't understand my handwriting, that's what we've done over here as well. That is the exact same solution. We've got 14.555. Now, if this is good, let's go on to problem number 3. Problem number 3, it actually says that without actual division, show that 171 by 800 is a terminating decimal. Express it in decimal form. So if you remember, we had this discussion in our previous class on part 2, where we said that a terminating decimal should always be explained in 2 raised to n and 5 raised to m format. Alright, these should be the only remaining elements in the denominator, and all the other factors should cancel out for it to be a terminating decimal. So now if you see 800, let's prime factorize 800 and see what are the factors of 800. It's definitely ending with 0, so it has 2 as its factor. It's again ending with 0, so it has 2 as its factor. It's definitely ending with 0 again, so it has 2 as its factor. It's ending with 0 again, so 2 as its factor again. Ending with 0, so 2 as its factor again. And then it's 5, so it's 5 factor and 5, so again 1. So basically this can be explained, that is your 171 by 800 can be written as 171 by 2 raised to 1 2 3 4 5 5 into 5 square. Now for me to make this a terminating decimal, what would I, so first of all, so since it has 2 square and 5 square alone in this, I would say yes, this is a terminating decimal. True. So yes, this is a terminating decimal. In order to describe how it is as a terminating decimal, what's the decimal form? I would have to multiply both by 5 cube, because that's the only way I would get 171 into 125 in my numerator, and I would get, since it's 5 raised to 5 raised to 5 and 2 raised to 2, it would be 10 raised to 5, and that would be 1 2 3 4 5. So that's 1 lakh. Sorry. 1 2 3 4 5, so that's 1 lakh. Okay, so now let's multiply 171 by 125 to see what number we would get. This is 5, 7 5s are 35, 3 5 are 5 6 7 8, plus 2 1s are 2, 7 2s are 14, 1 again, 2 1s are 2 3, and 171 multiplied by 171 would be just 171. 5 6 7 8 9 10 11 12 13 7 10 11 2. So that's going to be 21375 divided by 100,000. That's 0.21375, and that's the solution to this particular problem. If you go ahead and if you go ahead and see, that's the particular solution to this problem as well. So if you go ahead and see, that's the particular solution to this problem as well. It's 0.21375. And that's what I've shown over here as well, right? So alright, so now let's move to problem 4. Problem 4 says that show this particular fraction in its simplest form. So if you notice over here, this is a non-terminating number again, but this has 3 different digits that are repeating. Okay, non-terminating repeating number. So that a non-terminating repeating number can be expressed in decimal form. A non-terminating non-repeating number is difficult to express in its simplest form. Alright. so as a fraction. So now, how do we do that? We'll do it this way. So x is equal to 0.365, 365, 365, and so on and so forth. And that's your equation number 1. Let's multiply again. Multiply. Give me 1 second here because my handwriting has just gone to dogs. Multiply 1 by 10. We get 10x is equal to 3.65365, and that's equation number 2. So if you see, we cannot subtract, see again, 3 will have to be subtracted from 6, 6 will have to be subtracted from 5, 5 will have to be subtracted from 3, 3 will have to be subtracted from 6. This will again give us, if we subtract 2 and 1 right now, it's again going to give us a non-terminating number. So again, let's do this thing, multiply 2 by again 10. We get 100x is equal to 36.5365365, etc., and that's 3. Alright, so again at this point of time we cannot subtract either 1 from 3 or 2 from 3 because none of these have its first integers ending with 5, first decimal places ending with 5. Its second decimals don't end with the same number. Third decimals still don't end with the same number. So however we do this, we are going to get the same digit, same non-terminating number. So what we're going to do is multiply 3 by 10. And we will get 1000x is equal to 365.365, 365, 365, so on and so forth. And if you notice, this is 4th. Now, the funny thing to this is that now that you've done this, right, you know that this particular number and this particular number now have its decimal places ending with the same digits, and therefore you can do 4 minus 1 now. And what will that give you? That will give you 999x is equal to 365. That means x is equal to 365 by 999. We know that 999 is basically 111 into 9, so it's divisible by 111 and 3. Can we divide this numerator by 3? 6 plus 3, 9, plus 5, it's 14. 14 is not divisible by 3. So it's just going to remain, and we know 11, so 111, that should have been 333 or something. So that's also not going. So x is equal to 365 and 999. It's the simplest form in which we can express this particular fraction. If you go ahead and see the next page, that's what we've got over here as well. We've just done the same in a bit more readable format for you. So that's what we get over here as well. At any point of time, if you want to read this particular page while I am going on with the chapter in view of speed or in view of ensuring that we don't lag behind a lot, please pause and take a note of this page if you want to. All right. And all right, so let's go to the next problem. That's the 5th problem in today's session. So the 5th problem is a bit on the other side. So whatever you saw till now was on the rational numbers and trying to prove that, or trying to show whether a rational or non-terminating number could be explained as a fraction or as a rational number in the p by q format. So that's what it was dealing with. Now we're going to work with irrational numbers. So this one says, prove that root 3 is irrational. If you remember, we did a question very similar to this in our previous class, and that was also proving irrationality of a number. So now let's, to work with this particular problem, let's consider that root 3 is a rational number. Root 3 is a rational number. Hence, root 3 has to be of the form a by b. If you cross multiply this, you're going to get b root 3 is equal to a. Correct? Squaring both sides. You're going to get 3b square is equal to a square. Since 3 is a factor of a, it should be a factor of a square. If you remember, we had seen this particular theorems. This particular theorems. I just said, since 3 is a factor of a square, it should be a factor of a as well. So if you remember, we had seen this particular theorem in the previous class, wherein we had said that since a is a factor of, or some number is a factor of its a square, we had proved that it would be a factor of its non-squared number as well, because it would be one of the factors. If a square is equal to p1 square into p2 square into p3 square, and you know that 3 is one of those factors, or p is one of those factors, that's p is, then p has to be either p1, p2, p3, p4, p5, or so on and on, so till pn. Therefore, since a is already made up of p1, p2, p3, p4, p5, and so on and so forth, therefore one of those factors is p, and therefore p is also a factor of a. We're actually working in the same theorem here, and that's why I said that's an important theorem for you to understand, because we'll directly apply that. Since that's a theorem, we'll directly apply that in all our problems. So now we know that 3 is a factor of a as well, so we could therefore assume that a is equal to 3c. Now this is 1, and let's say that this is 2. Substituting, forgive my bad handwriting, but 1 into, what do we get? We get 3b square is equal to 3c whole square. That's b square is equal to 3c square, and therefore 3 has to be, if you see over here, that's, I'll just move to the top because I don't have a lot of space. 3 is a factor of b square and b as well. True? But what did we assume initially? That root 3 is a rational number, wherein root 3 is equal to a by b, where b is not equal to 0, and a by b have only one factor, that's a, one in common. So a by b is in simplest form. That's how it would be a rational number. But it has now 3 which is in common. And that's basically because root 3 is, our initial assumption was wrong. That is, root 3 is not a rational number. So root 3 is irrational. We have proved that. Alright, so that's the solution to this particular problem. If you go to the next slide, that's what I've written over here. Let's consider that root 3 is a rational number. Then there exist two integers a and b such that root 3 is equal to a by b, where a and b do not have a common factor other than 1. We square on both sides, we get 3b squared is equal to ac square. So therefore a square, therefore we understand that 3 is a divisor of a square, and therefore a is equal to 3c. Now if we substitute that, we get b square is equal to 3c square, and 3 is a factor of b square as well, and therefore this contradicts our original assumption that a and b do not have a common factor other than 3. This is because our original assumption that root 3 is a rational number is wrong. Hence root 3 is an irrational number. Alright, now let's go to problem 6, which is a little on the similar lines but a little different at the same time. So 3 plus root 2 is irrational. So we already read about this. If you remember, there was a note that we had dealt with in the previous class which said that a sum of a rational number and an irrational number is always irrational, and that's what we're trying to prove over here. So 3 plus root 2, let's consider that it is a rational number and it ends in a by b. It's of the form a by b. Alright, so that will mean that root 2 is equal to a by b minus 3. Right? Over here, since a by b is a rational number where b is not equal to 0, and a and b don't have a factor common other than 1, both of them are like some sort of a whole real number, so a by b minus 3 is also a rational number. But we know that root 2 is an irrational number, right? Just now this particular thing says that root 2 is a rational number because it is one rational number minus another rational number. It has to be a rational number. But we know that root 2 is an irrational number. Right? Why does this contradiction arise? Why do we get that root 2 is an irrational number? That's because our original assumption that 3 plus root 2 is equal to a by b is a rational number is wrong. Actually, 3 plus root 2 is an irrational number. Because we assumed at the beginning that it is a rational number, therefore we decided otherwise, see, if we had assumed that this was an irrational number, we would never have written this in an a by b form, and we would have written this in some irrational form. Then we would have got that some irrational number minus 3 would have been an irrational number root 2, and that would have been in line. But because we assumed that this is a rational number, because we assumed the opposite, we got that root 2 is a rational number. But we know that root 2 is which is evident from a rational number minus a rational number. But we know that root 2 is not an irrational number. If you want, you can go back and see the previous theorem for that. So root 2 is not an irrational number, and therefore it's not a rational number, and therefore 3 plus root 2 is also not a rational number. Our previous assumption was wrong. You see, that's what we've explained over here as well. 3 plus root 2 is equal to a by b, where a and b are rational numbers. Root 2 is equal to a by b minus 3. This means root 2 is a rational number, but we know that root 2 is an irrational number, and therefore 3 plus root 2 is a rational number is wrong. It is an irrational number. Alright? I hope you have understood this particular problem. So let's go to the next problem. The next problem is problem number 7. That is basically about the fact that 2 plus root 5 is irrational. Now, just like we did in previous problems, let's consider 2 plus root 5 is a rational number. And a rational number has to be of the form a by b, where b is not equal to 0 and a and b have no factor other than 1 in common. True? Which means root 5 is equal to a by b minus 2. Now, since a by b is a rational number and 2 is a rational number, root 5 should also be a rational number. But we know that root 5 is an irrational number. Therefore, why is this contradiction arising? Because our original assumption that 2 plus 5 root 5 is a rational number is wrong. 2 plus root 5 is irrational. True. So if you see, that's what I've written over here. 2 plus root 5 is equal to a by b. Root 5 is equal to a by b by 2. And we know that root 5, this shows that root 5 is a rational number, but we know that root 5 is an irrational number. Therefore, 2 plus root 5 a rational number is wrong. That's not the right assumption. We should actually say that 2 plus root 5 is an irrational number. So if you see, it's a pretty your irrationality has a pretty common set of problems that you get. So it's better to be aware of all these sort of problems so that we are not stumbled. And these are the sort of problems that you could solve at get-go, and so that you can devote your time to more confusing problems if there are any, right? Alright, so next one is 5 plus 3 root 2 is irrational. Alright, so again we go through the same steps. That's, we assume first the contradiction that 5 plus 3 root 2 is rational, and therefore 5 plus 3 root 2 is equal to a by b. This means that for root 2 should be equal to a by b minus 5, because I'll take the 5 over here, a by b, and this 3 will come in the denominator. So 1 by 3 into a by b minus 5. Now, however you write this, if you think that a by b is rational, where b is not equal to 0 and a and b are some form of real numbers which don't have any number apart from 1 in common, then you should know that you are subtracting a rational number from another rational number and then dividing that by a rational number. So root 2 has to be a rational number. But we know again, root 2 is an irrational number, right? We know that root 2 is an irrational number. Hence, root 2, hence our initial assumption is wrong. Hence, that is 5 plus 3 root 2 is an irrational number. If you see, that's what I've shown over here. It's the same steps. I've written it down the same way, and the same proof has been given over here. Please pause and have a look at this in case you have a little bit of a difficult time understanding my handwriting in the previous area, and please go through this. Now, meanwhile, let's move on to problem number 9. Problem number 9 says that prove that 2 minus 3 root 5 is irrational. So how do we do that? Let's again assume 2 minus 3 root 5 is rational, and 2 minus 3 root 5 is equal to a by b, where b is not equal to 0 and a and b have no factor in common apart from 1. True? Very nice assumption to make. But that means 2 minus 3 root 5 is equal to a by b could also be written as root 5. So I'm going to take this 3 root 5 here, and then I'm going to basically make it as 2 minus a by b, and then I'm going to take 3 down and I'm going to multiply that over here, right? So this would mean that you have a rational number minus another rational number divided by a rational number. So your root 5 is a rational number. But we know this is wrong, right? So this is because our initial number assumption was wrong, and 2 minus 3 root 5 is actually irrational, right? And that's how we would prove this particular problem. So if you have any problem understanding this particular solution, that's what I've done over here. That's the exact steps that I've done over here. So you can look through this in case you have any doubts. Moving on to the next problem. The next problem is problem 10, which says that prove that root 3 plus root 5 is an irrational number. That's a nice one to have. So basically I'm saying root 3 plus root 5 is equal to a by b, where b is not equal to 0, and a and b are some real numbers that don't have any factor in common other than 1. And this means that root 3 plus, we're basically assuming that root 3 plus root 5 is rational. So now let's square, so let this be 1, okay? So for us to prove, if you've noticed in all our previous problems, we've proved that a number is rational or rational by basically proving that it's either a multiple of just rational numbers, or divided by rational number, or multiplied by rational number, or just added by rational number. So it just has rational numbers in its equation. So to prove that, what we would have to do is solve this so that there would be just one rational number in the equation, right? How would we do that? We would square both the sides. So squaring both sides, what would we get? So we would get root 3 plus root 5 whole square is equal to a square by b square. Root 3 plus root 5 of the whole square. This is of the form a plus b whole square, which is of the form a square plus 2ab plus b square. And therefore, this can be written as a square. That's root 3 whole square plus root 5 whole square plus 2 into root 3 into root 5 is equal to a square by b square. So this becomes 3 plus 5, right? 8 plus 2 root 3 into root 5 becomes root 15. So you can subtract, you can multiply the roots within the numbers within the root. You can multiply that. So this becomes a square by b square. So in short, you could write, sorry about that, you could write root 15 is equal to a square by b square minus 5. 3 plus 5 is 8, right? Into 1 by 2. So that means that since this is a rational number and this is a rational number and this is a rational number, we could say, or even you could write this as, give me 1 second there. just in case you have a doubt about a square by b square, you could also write this as a by b whole square minus 8 into 1 by 2. So since this is a rational number, this is a rational number, this is a rational number, root 15 should also be a rational number, but we know that root 15 is an irrational number because it's just made of 5 and 3, and that's not a perfect square. So it has to be an irrational number, and therefore that contradiction is arising because our initial assumption that root 3 plus root 5 is irrational is wrong. If you go over and see the next screen, yeah, that's what we have done over here as well. All right, but we've done it in a little different format, wherein we have said we've separated this and then squared it. So you can do it either way. Either way, you're just going to get an explanation that contradicts your previous assumption. So if you get that, you're good to go. This is a slightly different approach to the same problem, but you can do either way. All right. Take a look through this particular problem. If you see what we've basically done is I've separated the root 3 and root 5 here and then done the squaring. So you will just get root 5 remaining and not root 15 anywhere. But either way, you will just get a square, and this is a by b whole square. Okay, so you're just going to get a rational number plus rational number divided by rational number. So root 5 has to be a rational number, but we know that's wrong. Root 5 is not a rational number. So that's how this particular solution works. Now let's go to problem 11. Problem 11 says that prove that 2 root 3 minus 1 is an irrational number. So again, as we did previously, 2 root 3 minus 1, let it be considered as a by b, where a by b, that is where b is not equal to 0 and a and b don't have any factors in common other than 1. So because we are considering 2 root 3 minus 1 to be rational number. So now root 3 could be written as a by b plus 1 into 1 by 2. Now we know that a by b is a rational number, plus 1 is a rational number, this is a rational number, and therefore root 3 has to be a rational number. But again, we know that root 3 is not a rational number. Why? Because root 3, because that's the general idea. Any root of any number, any nth root of any number that's not a perfect number to the power n, or then that particular number is an irrational number. We know root 3 is an irrational number because it's not a perfect square in this case, and therefore that particular contradiction arises because our initial assumption that this particular 2 root 3 minus 1 was rational was wrong, and therefore 2 root 3 minus 1 is irrational. So that's exactly what I have explained over here. All right, so we can go through this if you have any other questions. And we're coming next to the problem number 12. Problem number 12 says that prove that 4 minus 5 root 2 is an irrational number. Now, by now, all these problems should be pretty similar to you. So again, you're going to prove that a by b is a number that is a rational number. So 4 minus 5 root 2 is a rational number where of the form a by b, where b is not equal to 0 and a and b don't have any factors common other than 1, and both of them are real numbers. So this means that you could say that 4 minus a by b is equal to 5 root 2, implying that root 2 is equal to 1 by 5 into 4 minus a by b. True? So that's very good. That means that root 2 is equal to 1 by 5 into 4 minus a by b. So since this is rational, this is rational, this is rational, you would expect root 2 to be a rational number. But we know that root 2 is an irrational number. All right, and therefore that particular contradiction arises again because our initial assumption that 4 minus 5 root 2 is a rational number was wrong. It's actually an irrational number, hence proved. So this is again what I have shown over here. All right, just go through this in case you have a difficulty understanding my handwriting. Now let's go to the final problem, problem number 13, which is saying that prove that 5 minus 2 root 3 is an irrational number. 5 minus 2 root 3, let's consider that to be a rational number, basically a contradiction of what we had said earlier. So let's consider this to be a rational number. This means 5 minus a by b into 1 by 2 is equal to root 3. Since this is a rational number, this is a rational number, this is a rational number, this has to be a rational number, but we know that root 3 is not a rational number, it's an irrational number. And that contradiction arises again because our initial assumption that 5 minus 2 root 3 is a rational number is wrong. Hence, 5 minus 2 root 3 is an irrational number. True? That's how we're going to prove this, and that's the particular solution that we've written over here as well. Alright, with this we come to the end of all the CBSE problems that have been asked in the previous question papers. Some of the CBSE problems we've solved. We have many such more tests or assignments for you in vyans.org, so please do visit our site and try them out to see how well you have understood the concepts that we've taken in this particular class, and do well in your studies. Thank you and have a wonderful day.